Hi, it's Ms. Moser here with a few helpful bits for you on calculating net forces. So, you already know that anytime you're doing a net force problem, you're going to start off with a free body diagram where we do a generalized drawing of the object. We place all the forces onto the object as though they are originating out of the center of the object, and we label them as appropriate. That's the easy part. Now, we're going to move into some more interesting bits and some helpful tidbits to get you through net force problems. We're going to start off with a sample problem from page 132 in your Holt Modern Physics textbook. It's sample problem 4A. A drafting table, which is inclined at 35 degrees, and that the forces acting on it are what they call the force of the table on the book. What we've established is normal force, the force of gravity acting on the book, and the force of friction acting on the book, preventing it from sliding down the surface. So, to start off with, a few notes. We haven't talked about normal force yet, but you should know that it's always going to be directly perpendicular to whatever surface is exerting it. So it's going to be 90 degrees from the surface, while gravity is always going to be straight down towards the center of the earth, even when you're on a slope. Friction always opposes motion, so it's always going to be in the opposite direction of whatever direction you think the thing is going to move. But those are all really topics for a later date. Right now, the things that I want to get to are how to resolve that gravity. We talked a little bit in class about how when we have an object like this that's on a slanted axis, if we leave our plain old XY axis that we usually use in place, then it causes us to have to resolve two of the three vectors, and it makes our work much more difficult. But, and this is totally legal, if we tilt the axes so that we just make the x-axis run along that slanted surface, we only have to resolve one of our vectors. You can see my normal force is a little bit off the axis, but I can fix that. We only have to resolve one of the vectors because the other ones line up on the x and y axis 100%. And that makes our work much easier. So that's a standard method that we use when doing anything with a sloped surface. Now, how do we figure out this angle in here? So to do that, I'm going to run you through a little algebraic or geometric exercise. We're going to start off with a sloped surface, and for the sake of simplicity and keeping this a fairly low-level demonstration, I'm going to make this 30 because it makes the math easy for me. So, if we're tilting our axis, we can now visualize our Cartesian coordinates as these set of lines, and I'm actually going to move these down so that they're directly superimposed on our sloped surface. There we go. So it's safe to say we can all agree that if we run a line from that starting point of our slope out to where it intersects the y-axis, and we know that this angle is 30, and we know that this angle is 90, I think we'd all agree that this angle is 60. Yes? Good. If I add a little line right here that again intersects the y, starts at the x-axis and intersects the y-axis, I think we'd all agree that since this is 90, that overall angle, the little interior angle here has to be 30 degrees. That's a good thing. So then, this could in fact be our gravitational force line. That could be the force of gravity acting directly downwards on an object. Okay, you say, but I don't care about what angle gravity makes with the y-axis. Yes you do. So, if that's a 90-degree angle, then the little angle in here has to be 60. Okay, we're getting somewhere, we're getting somewhere. I'll label that there. So if that's 60, and we're going to get rid of this, and we break apart the gravity on the x and the y axis into these component pieces, and we're in agreement that other than my bad drawing, this is 90. If we know that this angle is 60, then this angle here must in fact be 30 degrees. It's a tricky little bit of geometry, but it's proof that the angle between that direct downward force of gravity and the y-axis is in fact 30 degrees. You can also see it here in this angle, but we're accustomed to taking the components of gravity out here behind gravity. So all of that is just to say that when we look here at the force of gravity, and we need to break the force of gravity into its component pieces, an F of Gy and an F of Gx, we're going to use trig functions that relate to this angle, and that this angle is in fact the same as the angle at the base of our slope. So, we've got our drawing, we know a little bit about how to find our angles, and we always start off with a sum of forces. It's easy to start off with a sum of forces where you're pretty darn sure they equal 0. And since this book is not spontaneously rising into the air, nor spontaneously crashing down into the earth, I'd bet you even odds that the sum of forces on the y-axis is 0. Cool. The only forces that we have on the y-axis are the normal force, which is acting up, and we have the force of gravity on the y-axis, which is acting down. We know that they must be equal because, again, the book isn't spontaneously rising into the air nor crashing through the table down into the earth. Okay, we're going to set that aside. Now we're going to look at the forces on the x-axis. And the first force that I see on the x-axis is the force of friction. And that's pointing up the slope. And then I have the force of gravity pointing down the slope. I'm sorry, gravity on the x. So how do I create an expression for force of gravity on the x? Well, everything that you learned about vector analysis in the last chapter. This is a right triangle. There's my hypotenuse. There's my angle. And the force of gravity on the x-axis is opposite the angle. So in fact, the force of gravity on the x-axis is just equal to the force of gravity times the sine of 35 degrees. I was given the force of friction, so I'm going to plug that in. So I know that the force of friction, and I should always list my variables, of course, is 11 newtons. What is the force of gravity on this book? Well, we're told that it's 22 newtons, and later we'll learn how to calculate that for ourselves. So, what we now have is that the sum of forces on the x, which is going to turn out to be the net force, is equal to 11 newtons up the slope plus 22 newtons times the sine of 35 degrees down the slope. Now, here's the interesting part. I'm adding these together. It's a sum of forces, but they're in opposite directions. So one of them has to be a negative. Once you start calculating force of gravity on your own, this problem will solve itself. But for now, we're just going to note that down the slope, which also happens to be in the Cartesian negative direction, we're going to call a negative. So what we're going to end up with is 11 newtons plus a negative 12.6186816 newtons. And that's what you get when you have 22 times the sine of 35. So my final net force, which is going to be equal to the sum of forces on my x-axis, is 1.6186816 blah blah blah, if you have more spaces on your calculator, newtons. With sig figs, and we have, I believe, only 2 sig figs, so that gives us 1.6 newtons of force. And it's important to remember that force is a vector. So you have to give a direction for that. And in this case, you can say at 35 degrees above the horizon, but that could be up or down the slope. So in this case, you'll also want to make sure that you specify down the table. And a lot of sources will just say 1.6 newtons down the table and leave off the 35 because we know that the 35 degrees is the slope of the table. The question that you were asked is whether or not the book would remain at rest. And in fact, the book does have a net force on it. The forces on it are not all balanced. And because of that, the book will slide down the table. Okay, that's it. You should be able from there to go ahead and get started on the 4A problems. They are all assigned.